Hello. Welcome to this review of quantitative methods. This presentation was originally part of the Mixed Methods Workshop sponsored by the Stanford Surgery Policy Improvement Research and Education Center, or S-SPIRE. My name is Amber Trickey. I'm the Senior Biostatistician for S-SPIRE. The broad goal for this Mixed Methods Workshop is, of course, to enhance mixed methods research. Researchers need to expertly blend quantitative and qualitative methods, tailoring their approaches to fit the research questions. Today, I will provide a brief overview of quantitative methods with the goal of informing your mixed methods research, including your joint displays and other approaches to integrating qualitative and quantitative results. Today, I will cover a broad overview of the fundamentals of quantitative methodology, including study design, hypothesis testing, analysis, and p-values. Because my focus is in health services research, my examples are selected from this field, but these methods can be applied to numerous diverse research areas. We can apply quantitative research to statistically describe a population, health event, functional status, interaction with the healthcare system, almost anything really. Quantitative methods are used to test theories and formally evaluate hypotheses. We often hope to generalize our results to a broader population and draw inferences about cause and effect. Quantitative study designs come in three broad flavors. Descriptive studies may not formally test hypotheses. They focus on precisely measuring certain aspects, such as incidence and prevalence studies in public health. In health services research, descriptive studies may aim to describe healthcare utilization, cost, or patient outcomes. Observational analytic studies do test hypotheses, but they do not control any aspect of the research experimentally. For example, survey data are often used in social sciences, including in health services research. Other observational studies are also common in health services research due to the availability of claims data, electronic medical records, and clinical registries. Retrospective and prospective cohort studies and case control studies are examples of observational study designs. Experimental designs, such as randomized controlled trials and implementation studies, involve some control of the experimental design by the investigators. Another helpful framework for thinking about study design is the evidence pyramid. Small, purely descriptive studies are at the bottom of the pyramid, along with expert opinion. Analytic studies that formally test hypotheses with an intervention or exposure of interest, as well as a comparison group, provide higher levels of evidence than descriptive studies. While randomized controlled trials are the highest level of evidence for analytic studies, don't forget that systematic reviews and meta-analyses, those studies of studies, are at the top of the evidence pyramid. This is because one study is never enough evidence. Strong causal inference requires a demonstration of consistency and coherence across multiple studies over time. It will be helpful to talk about a specific example as we work through these quantitative concepts. Imagine we're designing a hypothetical retrospective observational study. If we want to compare surgical versus non-operative treatment, in other words, antibiotics, for uncomplicated appendicitis, we might quantitatively measure success as not returning to the hospital, or even the ED, within 90 days of the admission. In this mixed methods study, we will also interview patients at our own hospital to understand their experiences. In designing or evaluating studies, we should consider both the external and internal validity. External validity relates to the generalizability, or the ability to apply the study results in other populations, systems, or locations. External validity is typically not related to the statistical analysis, but is strongly influenced by study design elements. For example, which patients, participants, or providers are included. We might also ask, how is the intervention or the treatment implemented in the study? And how close does it come to the real-world conditions? Internal validity relates to finding the true cause and effect relationship. This can be influenced by study design as well as statistical analysis decisions. Which variables are collected in the study? Is any important information missing? Unmeasured confounders, which we'll discuss on the next slide, can influence the internal validity of the study findings. Data analysis methods also affect the internal validity of the study results. Decisions such as variable selection, multiple regression, moderation and mediation analyses should be carefully considered with a biostatistician. Now we can break down a typical hypothesis and analysis into 3 variable types. Dependent variables are the outcomes of interest, the effects we want to measure. Independent variables are the predictors, or the causes, though we don't often have strong enough causal evidence, but that is what we're thinking. We want to build evidence toward understanding this causal relationship. Covariates, or confounders, influence this cause and effect relationship that we want to understand. Technically, confounding variables must have a statistical relationship with both the DV and the IVs. Sometimes, potentially confounding variables can be included and maintained in the model for statistical adjustment in order to compare with the results of other research. In our hypothetical appendicitis example study, our outcome of interest, the dependent variable, is 90-day return to the hospital or ED. The independent predictor variable is treatment, surgical versus non-operative. One potentially confounding variable we might adjust for or stratify for in the analysis could be insurance status. Insurance could affect the independent variable, treatment decision, and it could also affect the dependent variable, returning to the hospital. I would recommend putting some thought very early in the study design into which potential confounders will be important to consider. Variables can be measured on about 5 different scales, ranging from the highest information content at the top of this table with continuous variables, to the lowest information content at the bottom of the table with dichotomous 2-level variables. I won't read the whole table in the interest of time, but this summarizes different characteristics and descriptive statistics based on the scale each variable is measured. In your study design, you should collect information toward the top of the scale as much as possible. You can always categorize down the table later, converting continuous variables to categorical variables, but you can never recreate the more precise continuous measures higher in the chart. In analyzing data and reporting the results, we will utilize multiple statistical measures. The central tendency we think of most commonly. The mean, median, or mode are appropriate for different measurement scales. Although not as commonly recognized as central tendency, the variability or dispersion of data is very important to understand, describe, and analyze. Dispersion is the extent to which data points in a distribution depart from the center and each other. The standard deviation is an appropriate measure to describe normally distributed data, whereas interquartile ranges are usually better for non-parametric distributions. Degrees of freedom are related to the number of independent variable factors or levels which are included in the analysis. The statistical model's precision, fit, and performance are related to the degrees of freedom, which are derived directly from the IV measurement scales. Relationships between variables, or effect sizes, are often the main study results supporting the research hypothesis. Examples include odds ratios, hazard ratios, and correlation coefficients. The precision, typically described by the 95% confidence interval, is based on the sample size and variability. To maximize study precision, increase the sample size. And finally, the p-value conveys similar information to the 95% confidence interval. Some statisticians would argue that the p-value suffers weaknesses compared to 95% CIs, so the p-value should be de-emphasized. We'll talk more about the exact definition of the p-value and its limitations in a moment. Before we dive into the options for statistical analysis, let's review the null and alternative hypotheses. The null hypothesis is the default assumption for superiority studies. The null hypothesis is that the treatment or intervention has no effect. In other words, there is no difference between study groups. In our appendicitis example, the null hypothesis would be there is no difference in the 90-day hospital return rates between our surgical and non-operative treatment groups. This is the default assumption, but not what we actually believe. The null hypothesis acts sort of as a straw man, assumed to be true so that we can knock it down as false with evidence from our statistical tests. The alternative hypothesis is what we believe, the assumption being tested, that the group or treatment or intervention has some effect. For appendicitis, the alternative hypothesis is that we expect to observe a different, maybe a lower, rate of hospital return for appendectomy patients. Keep in mind that for non-inferiority studies, which are increasing in popularity in the literature, these two hypotheses are reversed. The null hypothesis assumes a difference, and the alternative proposes no difference in outcomes within a pre-specified range. Considering one versus two-tailed hypothesis tests, we generally always want two-tailed tests. Let's imagine we've calculated our statistic of interest, the t-statistic. In this case, we're going to use a continuous variable, the number of days to hospital return. We would measure this among those who return to the hospital within our 90-day period after their discharge for appendicitis. Our null hypothesis would be that the mean days to return are equivalent in the surgery versus non-operative patients. The null hypothesis is represented by a t-statistic of 0 in the middle of this distribution. The two-sided alternative hypothesis tests for effects in both directions, that the mean days are higher in the surgery group and that mean days are lower in the surgery group. If we were to use a one-sided test, we would only evaluate the association in one direction. If the association goes in the opposite direction, the p-value will not be statistically significant, and we would miss this association. Two-sided tests are almost always preferred. They set a higher standard for comparison to evaluate the effect in both directions. We are concerned about two types of errors in hypothesis testing: false positives and false negatives. Type 1 errors are the false positives, finding an effect that is not actually true. These errors occur due to random, spurious associations in the data that are not generalizable to the broader population that the sample represents. Repeating the study in another population with the exact same inclusion criteria would have negative results. We typically, and somewhat arbitrarily, set the type 1 error probability, or alpha, equal to 0.05, or a 5% probability of committing a type 1 error. We'll come back to type 2 errors in a moment. The p-value has an important place in quantitative research. but many statisticians believe it's overrated. Jacob Cohen reminds us that the primary product of research inquiry is one or more measures of effect size, not p-values. The definition to keep in mind is that the p represents the probability of finding the observed or a more extreme test statistic if the null hypothesis is true. The p-value assumes the null hypothesis is true, that there is no difference between groups. Phrased another way, p is how likely we are to find a difference so extreme in our data if there were actually no difference between the groups in a broader sense. So the p-value measures evidence against the null hypothesis. The smaller the p-value, the larger the evidence against the null. And we reject the null hypothesis if p is less than alpha, the probability of type 1 error. But there are numerous pitfalls with p-values, which is why many statisticians believe they are overrated. To avoid these potential pitfalls, keep in mind the statistical significance of the effect does not explain the effect size. p.05 is an arbitrary cutoff, and this continuum is not truly binary. Never report just the p-value. You should always include the descriptive measures to capture the meaning of the effect size. As Jacob Cohen pointed out, effect sizes are the true products of research inquiry. Statistical significance does not equal actual clinical or educational or scientific significance. And finally, p is highly dependent on sample size. If a study is underpowered, the p may not be a true representation of the presence of an effect. Here are a few examples of some common types of analyses and how these might relate to our appendicitis questions. In a purely descriptive study, we might ask, how many patients return to the hospital within 90 days of admission for uncomplicated appendicitis? Measures of central tendency could include the median and mean days to hospital readmission for appendectomy versus non-operative appendicitis patients. One relationship of interest could be to explore whether insurance status is associated with the selected treatment, operative or non-operative management. To test for group differences, which is the main hypothesis of the study we proposed, we are going to evaluate whether patients treated with antibiotics are more likely to return to the hospital within 90 days of discharge. Correlation analysis of two continuous variables might include assessing whether length of stay and surgical duration, op time, were correlated in patients who underwent appendectomy. A multiple regression model could be calculated to determine which patient factors are independently associated with returning to the hospital. For example, in addition to the treatment type, surgery versus non-operative, we might want to look for relationships by patient characteristics as well, such as age, sex, and insurance status. We could account for all of these in one model with multiple regression. And finally, factor analysis might be useful if we are constructing a scale to measure appendicitis treatment decision satisfaction. When choosing an appropriate statistical test for your research questions, there are a few factors to consider. This decision tree is complicated, so I will not enumerate each statistical test, but you can pause the video and review in detail if you want. These are some of the options that you or your biostatistician will be considering for your analysis. Briefly, the statistical tests are chosen according to the number of independent variables you want to analyze, the measurement scale of the IVs, are they continuous, categorical, binary? If you have groups within your study, it's important to determine whether the groups are independent or dependent. Many studies have independent groups, such as our appendicitis example. Patients in the surgical treatment group have basically nothing to do with the patients in the non-operative management group. They are two separate groups of patients. However, if we had designed a paired analysis where patients were matched according to some criteria, or if the same patients were analyzed before and after an intervention, we would use the appropriate paired statistics to account for that dependence. Finally, the scale of the dependent variable is important. If you're analyzing a continuous dependent variable, you might consider linear regression, whereas a binary outcome would suggest logistic regression. Now to the other side of the error coin. Type 2 errors are false negatives, not finding an effect when one truly exists. This is due to an insufficient sample size to detect the true effect. Higher than expected variability may lead to this problem, and the only solution is to increase the sample size. We typically set beta, the probability of type 2 error, at 20%. Some studies may take a more cautious approach and set beta equal to 10% or 0.1. To avoid making a type 2 error in your study design, you want to ensure that your study sample size will provide adequate statistical power to answer your research question. Continuing with our appendicitis example, let's say we are now designing a prospective randomized study of non-operative management versus surgical treatment, and we want to assign patients in a 1-to-1 ratio per group to surgical versus non-operative management. In order to calculate the study sample size that will achieve adequate power, we need the following components. Statistical power is the complement to type 2 error. If type 2 error probability is 20%, then power equals 1 minus beta, or 80%. As we discussed earlier, the type 1 error rate, alpha, is usually 0.05, or 5%. The effect size can sometimes trip investigators up when conducting power and sample size calculations. This is because the expected effect size can be estimated in so many ways, and you may want to consider using more than one method in your power analysis and comparing the estimates between methods. Some investigators have pilot data in the specific study population, or have obtained administrative or clinical data to at least suggest the study measurements are possible. Other investigators may base their effect size estimates on literature review. Although the exact study design you may be planning is usually not available in the literature, that's why you are conducting the study, you can often find research similar enough to yours, studies that made similar measures in a similar population. Estimates from others' research in the literature can be very informative for power calculations. Another option for estimating your effect size for power is using the minimum clinically important difference, or the difference which would cause a clinician or a decision maker to change practice. Back to our hypothetical example. Let's say we scoured the appendicitis literature and found evidence that 90-day hospital readmission rates are 1% for appendectomy patients and 3% for patients treated with antibiotics alone. Given these components, power, alpha, our expected effect size, now we can calculate our sample size, the number of subjects required to detect this specific level of effect with adequate power. We calculate that we would need 1,538 patients, or 769 per group. All of this talk about statistical power is not at all meant to diminish small sample sizes. Small samples are completely reasonable and expected in qualitative approaches. So many mixed method studies may have smaller populations, especially in the early stages of the research. The best advice that I can give to account for small samples is to transparently express the precision of your estimates or the confidence intervals of your measures. Keep in mind that you are building evidence to inform power for future studies, so the efforts to create preliminary data are always worthwhile in my opinion. You will conduct future research with larger power using evidence-based sample size calculations in the planning stages. So in summary, I would like to share these 7 habits of highly effective data users that summarize many of the topics we've discussed today. First, you should always check data quality before quantity. All data are not created equal, and fancy statistics cannot salvage biased data. Describe before you analyze. Special data may require special tests, and improper analysis is going to give deceptive results. Accept the uncertainty of all data. All observations have some random error, and interpretation requires estimating the precision or confidence so that we can properly interpret the estimates. Measure error with the right statistical test. Qualify your positive results by the chance of being wrong, and qualify your negative results by the chance of having missed a true effect. Put clinical importance before statistical significance. Statistical tests measure error, not importance. So an appropriate measure of clinical importance must be checked every time. Seek the sample source. Results from one data set do not necessarily apply to others. And overall, we should keep in mind that science is a cumulative process. A single study is rarely definitive. I will leave these references up for a few seconds for extra reading on these topics. And I'd like to thank you for joining me today. I hope that this overview of quantitative methods will help you in your mixed methods research endeavors.